Günaydın. Okay, so let's start by what we have done last time. Morning. We defined a local isometry or isometry. Local isometry is a function from a surface to another surface. So of course it is differential. So that F star V inner product F star V is always, or W is always V dot W for V and W independent space of the surface M and for all so an isometry is something like this. A local isometry is a smooth map so that at any point, if you pick two vectors, you so G and W, let's say, and then their images at the point f of p. So what is this vector? This is f star v and f star w. The inner product of these two vectors is the same as the inner product of these two vectors. If f is a local isometry and if it's the diffeomorphism, then it's isometry. Of course, if f is a local isometry, it preserves inner product, therefore it preserves length of a vector. Therefore, a non-zero vector is never sent to a zero vector. An isometry is automatically has injected derivative. Now, the local isometry is F star injected and therefore surjective, of course, because both tangent spaces have the same dimensions, right? F star is a map. F star is a map from the tangent space of the first surface to the side tangent space of the second one. They are both two-dimensional vector spaces, and injective map is necessarily surjective. Therefore, it's an isomorphism. And therefore, by the inverse function theorem, it's a local diffeomorphism. So, inverse function theorem says that F is a local diffeomorphism. But the local diffeomorphism doesn't imply that F is a diffeomorphism. That's a topological condition. It has to be, moreover, one-to-one and on. So if local isometry is called an isometry. F is isometry F, of course. If F is also a diffeomorphism. Actually, it is enough to say that if F is a local isometry and if F is one-to-one and on2, then it's a diffeomorphism, of course. Because we know that F is a local diffeomorphism, so if it is one-to-one and on2, then it's a diffeomorphism. We defined distance, intrinsic distance, what was that? If you choose 2 points on the surface, we define the increasing distance between P and Q as the infimum of length of infimum of length of alpha. Alpha is a function or path, smooth and curve, such that alpha of A is P and alpha B is Q. So you take all the curves, and here this is just the alpha prime P non P. So it's length of the curve. And we showed last time that if F is a local isometry, then for any curve, length of alpha is the same as length of f of alpha for any curve. Therefore, if you have an isometry between two surfaces, then the intrinsic distance between these two surfaces, on these two surfaces are the same. So if it is an isometry, then the distance between 2 points on the surface M. So here I take the distance between point between on the surface M, and here the distance between these 2 points on the surface M, and these are the same for all PQ in M. Okay, so suppose you have one surface. Last time you have also seen that there is an isometry between the plane and the cylinder. So if you choose 2 points like this, then the distance between these 2 points is something like this. F of Q. So something like this. Okay. And these two distances are the same. Last time we also gave this example, and isometry was this. Let me tell you the isometry. Yeah. So F U V, let's say, or Fxy. Fxy is just R times cosine X over R, R times sine X over R, and Y. This is an isometry, and it preserves the distance. It preserves the distance, of course. And if you take a curve, let's say a line segment joining these 2 points in the xy plane, then the image of that line segment is a part of an helix. And if you compute that these distances, they are the same. I'll give one more example of a isometry. So last time we gave this example, another example is this. So local isometry of a ellipsoid onto a catalogue. So here is the map of x uv. This u times cosine v, u times sine v, and v. So it's the surface patch for the ellipsoid. One direction is going up and down, and this is the direction, the circular direction. So, and so is this. Okay. So it's like a turning ladder, okay? Sorry. If you increase u, then you go in this direction, right? If you increase b, you go both in this direction, and of course, the point also turns, right? So as you move up, the point moves upward and it turns, and this coordinate just goes in the radial direction. And catonate is the following surface. So something like this. Okay. And so y will be, so this is the following function: sine inverse sine hyperbolic inverse u, and then 1 plus u squared in square root cosine v, and 1 plus u squared sine v. A surface patch. Okay. And isometry between them, F is the isometry, and F is given by the following rule. F x in V is just y. So it takes this point to this point, okay? It's a map from R3 to R3, but it's defined on these two surfaces, and it takes this point to this point. Okay. Now, to show that it's an isometry, we have to just check that F star preserves the inner product, but that is the same thing as checking the elements of the surface patch coming from the inner product E, F, and G. So I have for this E and G, and for this I have bar, F bar, to show that F is an isometry is equal to show that these gauges are the same. Like this was also something we proved last time. So we just need to check the E bar, F equals F bar, and G equals G bar. Okay, now let's compute all these. So I need derivatives of the surface patch. X sub u is just cosine v, sine v, and 0. X sub v is just minus u sine v, u cosine v, and 1. All right. So what is X bar? Sorry, not X bar. Well, okay. This is just Y bar, Y sub u. So E, F, and G for this coordinate patch. Sine inverse. What is the derivative of sine inverse? Hyperbolic, sine hyperbolic inverse. Let me check. I don't remember. Well, I didn't write it down. Okay, so let's figure out what's the derivative of sine. So derivative of sine hyperbolic. What is this? This is just cosine hyperbolic, right? And derivative of this is this one. So if you let f of x sine hyperbolic x, f inverse x is sine hyperbolic x inverse. So derivative of this is just 1 over derivative of f. Derivative of f inverse is this. So it's just 1 over cosine. So derivative of this is just cosine. So 1 over cosine hyperbolic x. Okay, so what is this then? This is just 1 over cosine hyperbolic x or u cosine hyperbolic u, and then derivative of this with respect to u, it is just 2u divided by 2 times square root of that, so it is just u over square root of this, and then cosine v. And then derivative again. So this sine v. What about derivatives with respect to v? Well, the first one is 0. The second one is just minus sine. And that is cosine. Okay, so let's compute now. Plus x sub u times x sub u, so it's just 1, right? we take that product of this itself, which is 1. F is just x sub u dot x sub v. So it is, I guess, 0, right? And G is x sub v times x sub v. It is u squared plus 1. So 1 plus u squared. All right. Now, what about E bar? So this is x sub u bar, x sub u, or y sub u, y sub u. So it is just 1 plus cosine hyperbolic squared plus square of this plus square of this. Sine squared cosine squared is 1. So this is just u squared 1 plus u squared. Well, this has to be 1. Oh. We have to be here, I guess, careful. I shouldn't put y here, right? Okay, we have this. F inverse of f of x is equal to x. So when we take derivative, you have this derivative. So f inverse f of x. So, derivative of this compute with f of x is equal to 1 over. So this means what?
Derivative of f of x.
Efendim?
F türevi x değil mi? 1 bölü f türevi. Çin türevi.
Ha, şurası, tamam. Yani f'in bunun inverse'ünün içine şey koyduğumuz zaman f sin inverse of h sin hyperbolic inverse bunun içine f'i koyuyorum. F dediğimiz sin x, yani şunun türevinin içine sin x koyduğum zaman 1 bölü cosine, değil mi? Dolayısıyla buraya ben u dersem şunu olacak. Sin hyperbolic x ise matematical sin hyperbolic x. Sin hyperbolic x squared plus no minus plus cosine hyperbolic x squared is 1, right? So if this is u, then this is cosine hyperbolic x is just 1 plus sin hyperbolic x squared x. So it is 1. If this is u, then this is 1 plus u squared. So this is just 1 plus u squared.
Square root.
Okay, and that's squared. All right. So yeah, we have to be careful. This thing is just So when you take that product of this guy with itself, you get 1 plus u squared. So this is just 1. S bar x u bar times x u bar. So y sub u times y sub v. 0 there. And then this also gives us 0. And g bar is just x sub u bar, x sub v bar. So it is just 1 plus u squared. So you see they are the same, okay? Here I have 0, 1, 0 this, and I have 1, 0, and this case. So that is tamam mı?
So in this case, because of the factor, we don't need to write an explicit isometry. We can just say that.
Well, actually, we have the explicit isometry. So f is what? F is the map standing x of uv to y sub y uv. Okay.
Which is the parameter.
Yeah. I have one more definition. First, report. Okay. Let me change the board. A measurement from a surface onto another surface of surfaces is conformal if there is a smooth function lambda from m into non-zero real numbers so that norm of this norm of f star of a vector is norm of the vector times a scalar. For all we in the convex space and P. Of course, if it satisfies this, then it satisfies this, so norm squared, and therefore it actually preserves the angles between vectors. If it preserves this, it preserves also. So at any time in space, it's not an isometry, but it's a multiple of an isometry, like 2 times an isometry, okay, or 3 times. So it scales the vectors at each point with a different number. At some point, it multiplies the length of the vectors by 2. At some other point, it multiplies the vectors, length of vectors by some other real number, let's say 3. But this fact shows that it preserves the angles between them. So let me write as an exercise. conformal map preserves the angles between adjectives. So if there are two vectors like this, they are mapped at the point and suppose this vector is mapped to something like this, and the other one will be mapped to a vector like this. The lengths might change, but they are changed, proportionally. You multiply the lengths, let's say, by 2, okay? At some point. At some other point, you may multiply them by 3. But that actually gives us that the angle between the vectors doesn't change. So conformal is not an isometry, but it is something close to an isometry. Okay. All right.
Can we say conformal and isometry?
Yeah. Actually, analytic maps, for example, between two complex domains are conformal, right? If the derivative is not 0 of a complex analytic map, then they are conformal maps. Complex analytic maps preserves the angles. So actually, complex functions are very geometric functions, okay? And that makes them actually not complex, but simple, okay? They are more actually geometric, they are easier to work with, okay? Unlike real value functions. So if B and B prime are complex domains, a function between them, let's say another function, and if the derivative is not 0 at any point, at some, on this domain, then f is conformal. If it preserves the angles, then it preserves basically the geometry. It's like putting a picture in on a Xerox machine, and you photocopy it. But the thing is that the enlarging, scaling constant changes from point to point. Okay, so complex analytic maps are maps like that. Okay, intrinsic geometry of surfaces. What does this mean, intrinsic geometry of surfaces in R3? Well, we have been studying surfaces in R3, but now we will study properties of these surfaces, which solely belong to the surface, not the embedding, or not the way they are embedded into R3. Yani intrinsic geometriden kastedilen şey sadece o yüzeyin üzerinde yaşadığını düşünün. Diğer yani range'in içinde olduğunuzu unutun. O yüzeyin bir yerde özelliklerini embedding'den bağımsız olan özelliklerini çalışma işi. Intrinsic geometry. Okay. First, we have an easy observation. The connection form W12, which is of course equal to minus W21. This statement is this. This is the only one form that satisfies the first structure equations. And what were those equations? So these are equations we studied earlier. W21. So the statement is not that W satisfies this equation. We already proved that. We are claiming that W is the only form that satisfies these two equations. So if you have, let's say, two other forms that satisfies the same equations, then they must be the same as this two. Okay, that's the claim. It is not clear from this, so this form cannot be determined from this equation, right? This is wedge product. It's not a usual product, right? They are not functions, they are forms. But we will see that these two equations actually determines W uniquely. Okay, so that's the claim. Let's see why this is the case. Let's see the proof. Well, from the equation, we know that dW1 is equal to W1 to wedge W2. So if I plot these two vectors here, I get what? W1 to wedge theta 2 evaluated on the pair of vectors. Now, these are two one-forms. How would you evaluate wedge of two one-forms on two vectors? Well, that was computed as follows. You take the first one form, evaluate on these two vectors. So W1 to E1, W1 to E2, and then take the second vector and write the results as entries of a 2x2 matrix like this. And then you take the determinant. Okay, so what is the determinant? Yeah, but maybe before we take the determinant, let's see that, this is 0 because theta is the deuce of dual basis for this frame, and this is just 1. So the result is just W12 of E1. So the conclusion is that W12 of E1 plus V theta 1 E1 E2. Okay. Well, similarly, let's compute the other one. Let's use the other equation. Similarly, we take the proof E1, E2 is just W21 which theta 1 computed on E1, E2. So this is just the determinant of W1 to E1, W1 to E2, theta 1 of E1 and theta 1 of E2. This time, this gadget is 1 and this is 0. So the result is minus W1 to E2. Meaning that W1 to E2 is just minus d theta to E1. So you see, I have this one form, and the value of this one form on this vector is this number, and on the second vector of the tangent space basis vector, it is this one. Well, any linear form is determined by its values on a basis. And E1 and E2 form a basis for the tangent space. Therefore, W12 is determined with these values. If you had another form which satisfies these equations, okay, hangisi? Ha, şunu yanlış mı yazdım? Pardon. Okay, I'm sorry. This is 2-1, 2-1, 2-1, 2-1. Okay, so it is this. Since it is another minus, it will be this. Right, W12 is minus W21, so I can write this. Okay, now, so since E1, E2 form a basis for the tangent space, and W12, which is minus W21, is a linear map on TPM. W12 is uniquely determined by its values on E1 and E2. So this finishes the proof. Yani bir lineer fonksiyonu belirlemek için onu baz elemanlarında hesaplamanız yeterli. Biz de onu yaptık. Baz elemanlarındaki bu fonksiyonun değerleri bu şekilde bulundu. Bir de işte şu var. Başka bir W olsaydı, yani bir W bar olsaydı, onun da değerleri aynı olacağı için W bar'dan W aynı şey olacak. If you had a W bar, W tilde, which satisfies this equation, right? If you had a W tilde which satisfies the same equation, then W tilde would satisfy this and this one. But in that case, W and W tilde takes the same values on basis vectors. Therefore, they have to be the same linear objects. Okay. Okay. Okay, here's the lemma. Let me switch to the board 3. Okay, let's F from M to M bar do an isometry. And let E1 to be a tangent frame. We can extend this to a field of R3, tangent frame field of R3. How? We just need to plug another vector E3, and E3 could be taken to be just, of course, E1 wedge E2, right? Or cross product. But we don't need that. Field on M. If E1 bar, E2 bar is the transfer frame field on M bar via this F, then we have the following. First, theta bar is the same as 2 by 4 theta 1 bar. Theta 2 is just the pullback of theta 2 bar. And W12 is just W12 bar. But I is just F star of EI bar is just F star of EI. So transfer links, these are just the images of E1 and E2 under F. Okay. Okay, I'll put this. But let's do this in the second hour. I have only 1 minute left. So in the second hour, we will prove this, and then we will prove Gauss's theorem. Okay, let's have a break. Let us stop recording.